The first thing that we talk about in this class is limits. So you expect to be asked to find these types of limits. Okay. Questions expected. You find the limit. A, the limit of x equals to 2 of x squared minus 4 over x minus 2. B, you expect this type of questions, x3 minus 27 over x minus 3. C, we expect these questions go to infinity, x squared plus 2 over 3x squared minus 5x plus 1. Okay. So you expect this type of questions. Of course, some more are still coming, but as they come, we'll be answering them. So now we have space to do these three. So when you're asked to find the limit, in the case of question A, you are simply asked to substitute that value x. X goes to 2. So we want to substitute that to where there is x in this part. Now limits gives us a bit of some room to say, if you can't substitute, if you can't get a value direct, you can simplify the function and then substitute. So now in this case, if we try to substitute, we have 2 squared minus 4 over 2 minus 2, which will give us 0 over 0. We don't want this because that is undefined. So then what do we want? We want to rewrite this as the numerator now can be factorized. As you can see, it's a difference of 2 squares. So you can write it as x minus 2 multiplied by x plus 2. And then we divide by x minus 2. So then this part and this part will cancel. Then we'll have the limit as x approaches 2 of x plus 2. Meaning, where there is x now, we can substitute 2, and the answer becomes 4. So you get the logic there. X goes to 2. So where there is x, you put 2. It gives us undefined thing. What do? We simplify the function until when we substitute 2, now it will be defined. So we substitute 2 at that point, and we get 2 plus 2, which is 4, and 4 is defined. Okay. We go to B. B also, if you substitute 2 where there is x, we're going to have 3 power 3 minus 27 over 3 minus 3. Another 0 over 0 case. We don't want that. So what we do, we factorize the numerator again. But this time around, the numerator is a polynomial. Now, if you want to avoid memorizing, we can use synthetic division. Because you have seen when you substitute 3 in that polynomial, which is the numerator, then we're getting a 0. So 3 is a factor. So we can say, okay, we have found the factor. Let's pick the coefficients for that polynomial. 1 for x3, 0 for x squared, 0x, and then minus 27 the constant. 1 comes down, 3 times 1, you get 3. We have 3, 3 by 3, 9. We have 9, 3 by 9, 27. Minus 27 plus 27, 0. So now we can write the numerator, say the limit as x goes to 3 is going to be x minus 3 multiplied by x squared plus 3x plus 9 over x plus 3. Again, we have achieved our target to cancel out this part which makes things on the top. So that now we have the limit as x goes to 3 of x squared plus 3x plus 9. When there is x, we substitute 3 squared, 3 by 3 plus 9. So we have 9 plus 9 plus 9, which is 7. So what else do I want you to see? I want you to notice where I stop writing the limit. So before I substitute 3, I'll always have the limit 3. When I substitute 3 where there's x, I stop writing the limit because now I'm finding the actual limit. It's no longer a question, it's the answer. Okay? Then now we go to the other type of limit. C. C. Now look at C. C is saying x squared plus 4 over 3x squared minus 5x plus 1. But this time around, x goes to infinity. So there's one thing that we should all know that is used in this course. And that is the limit as x goes to infinity of any constant over x to any power is equal to 0. So for as long as you have a constant in the numerator and you have over x to any power, for example, 1 over x or 7 over x per 100, the limit goes to infinity, it will be 0. Okay? So now, how do we solve that? We go to the denominator and look for the highest degree. So the powers of x, the x that has the highest power is the x which has power 2. In the denominator, we factorize that power 2. Even if we don't find it in the numerator, we will factorize the same x power 2 from the denominator. So in the denominator, when you factorize, you are dividing in every other piece. So it will be 3x squared divided by x squared, you get 3. 5x divided by x squared, you get 5 over x plus 1 over x squared. The numerator, it will be 1 plus 4 over x squared. So again, it will be the limit now as x goes to infinity. So this part and this part gets cancelled. We have remained with 1 plus 4 over x squared over 3 minus 5 over x plus 1 over x squared. Now, the limit, you don't substitute infinity where there is x. You use this property here. Okay? So you can get, by evaluating, the limit as x goes to infinity of 1, that would be 1, plus the limit as x goes to infinity of 4 over x squared, that would be 0 over 3 minus 0 plus 0. So we get 1 over like that. So this is what we are using when we said for the horizontal asymptote, just look at the powers. At that time, we had not yet done limit. So we are looking. But this time around, what we are looking is coming from this point. So you can even show now that, oh, I'm just obtaining the limit of x goes to infinity. That is the horizontal asymptote. So for this time around, you don't just have to look at it, you have to show. When you say find the limit, you solve like this. Another set of examples. So let's call this one question 1. We're now going to question 2. Question 2 now. We'll have, again, find the following. A, the limit as x goes to 5x plus 1 over 10 plus 2x. B, the limit as x goes to infinity of 5 over 1 plus x. C, the limit as x goes to 5 over x squared minus 4x minus 5 over x minus 5. D, the limit at x equals to 0 plus absolute value of x over x. Okay. Again, solution. The first one, the limit as x goes to 5 of 5x plus 1 over 10 plus 2x. Let's see. Here, we start by substituting. So we have 5 times 5 plus 1 over 10 plus 2 times 5. That is 25 plus 1 over 10 plus 10. We get 26 over 20. Looks like 2 can go 13 times over 10 times. So that's the limit. Okay. So for long as that, when I substitute, I get a number. When I go ahead and just substitute. B, the limit as x goes to infinity of 5 over 1 plus x. Again, we go to the denominator and pick the highest degree x. So we have 1 over x plus 1. The same x we take up, so we have 5 over x. This x and this one gets cancelled. So that we have the limit now as x goes to infinity, 5 over x.
Obeying reposo. I already forgotten the response part of it. What are you going to do?
So even if there's no x up there, you check the same x coming from the denominator, you can factor it out up there. And then now we know this goes to 0, this goes to 0. So we have 0 over 0 plus 1, which is 0. See, the limit as x goes to 5. That quadratic there, we need to factorize it. So x squared minus 4x minus 5 is the same thing as x squared plus x minus 5, x minus 5, which is x plus 1 minus 5, x plus 1. So now we get x plus 1 multiplied by x minus 5. See? So we have x plus 1 and we have x minus 5 over x minus 5. So that this and this will cancel. Then we have a limit of x goes to 5 with x plus 1. Which is what? 5 plus 1, which is 6. So it could be a polynomial, a quadratic. We just factorize it. And then G for D, remember the absolute value of x is a function defined as x if x is greater or equal to 0, and minus x if x is less than 0. When they say from right, the meaning there is that you're looking for where x is greater or equal to that number. So in the event that the absolute value is defined this way, between these two pieces, from right, you pick greater. So come here now, having picked the greater of that absolute, it will be x over x. You forget about the minus x because that one is the limit from left. So from left, you would have picked less. If there was a minus there, one is plus. So now we want the limit as x goes to 0 plus x over x is 1. The limit as x goes to 0 over a constant is the same constant 1. You see? So there are hands here.
Sir, hello?
Yes.
Sir. Yes, so I was kindly asking if you could repeat on that one for the modulus. I haven't gotten it.
So the modulus is defined as, remember how we're defining modulus? It remains x if x is greater or equal to 0. Okay, so, and then it is negative x if x is less than 0. If you were to sketch the modulus, it will come out like this. You see? So if you are going to 0 from right, it means you're using this direction. And what you find in that direction is this x. If they say, so this is from right. If they say from left, you are going to be using this one because this is minus x. So between these two, when they say from right, you pick the positive one. When they say from left, you pick the negative. Or when they say from right, you pick greater or equal. When they say from left, you pick left.
Hello.
Um,
Okay, so sir, what you're trying to say is that what will determine whether we're going to pick the positive or the negative is the limit given.
is that plus there?
Sorry.
It's this plus in me.
Oh,
If you
okay.
find the
So we
plus there, you pick in the greater part. If you
okay,
find
so we pick
minus there,
any
you pick
number.
the less.
Okay.
You don't pick any number. You pick the function that is there.
Oh, okay. Yes, now I get it. It makes sense now. Oh, thank you.
With another hand. Oh, okay, let's do one hand, one down. Okay, another set of examples. We now want to introduce another term. Okay, so we introduce another term now. The term is continuity of functions. Okay, so the question is, when is the function continuous? When is the function continuous? When is the function continuous? It's a question which you're answering here. The first thing is f is said to be continuous at x is equal to c if the first thing, if f of c is defined. Number one. Number two, if the limit as x goes to c of f of x exists. Number three, if that limit as x goes to c of f of x is the same value as f of c. So for a function to be continuous, these three should happen. If one of them fails to happen, then the function is not continuous. Now let's go back to number two. When is the function said to have a limit? So the limit will exist if the limit as x goes to c left of f is equal to the limit as x goes to c from right. Okay. So there will be functions that will require you to pick the limit from left and from right. So if you're required to do so, and you pick from left and right, and you find that they are different, and the limit does not exist. If they're the same, the limit exists. Okay? Example. Determine if f is continuous at the given point. A f of x is equal to x plus 1 for x greater or equal to 2, that 2x minus 1 for 1 less than x less than 2, and the x minus 1 for x less or equal to 1. At x is equal to, at x is equal to 1, and also at x is equal to 2. Solution. So we want to check if the function is continuous at x is equal to 1. So let's start. At x is equal to 1. The first thing we check is what f of 1 is. What is f of 1? This is a piecewise function. You know f of 1. You go to the inequalities. Where you find 1 included, that is the piece that you use. So here we have x less or equal to 1 on this inequality. So you use this function. Okay? So we use 1 minus 1, it gives us 0. The second thing we do now is we find the limit as x goes to 1 from left. So we start from left. From left, you go to where x is less or equal to that 1. So you pick x minus 1. So you substitute 1 there, you get 0. You also get the limit as x goes to 1 from right. From right, you go where x is greater than 1. And so here x is greater than 1. So that one is too far from 1. That one is x greater than 2. So there's a space between 1 and 2. So you can't go where there's space. You go where there's no space. X bigger than 1. So you pick 2x minus 1 and find 1 minus 1. That is 1. You see? The limit, so now what we have observed is that the limit as x goes to 1 from left of f is equal to 0, which is not the limit as x goes to 1 from right of f, which is what? Which is 1. So the two numbers are not equal. That means that the limit as x goes to 1 of f does not exist. So if the limit does not exist, then we say f is not continuous at x is equal to 1. This is the conclusion. Okay? F is not continuous at x is equal to 1. What about at x is equal to 2? So I will check from here. The first thing we do is to check f of 2. Again, we look for a function which includes 2. So we have a function here where x is greater or equal to. So we will have 2 plus 1, which is equal to 3. The second thing we do is to find the limit as x approaches 2 from left. From left, we want x less than 2. We are using the middle one, 2x minus 1. That is 2 by 2 minus 1. That is 4 minus 1, which is 3. We also get the limit as x approaches 2 from right. From right, we want where x is greater than 2. So that will be x plus 1, which is 2 plus 1, which is 3. As you can see, the limits are equal. So this means that the limit as x goes to 2 of f is equal to 3. Lucky enough, that 3 is f of 2. Therefore, f is continuous at x is equal to 2. So for it to be continuous, all the properties must be satisfied. There are 3. By 11:20, do you have the lecture sheet for this topic? Okay. You don't have yet. Okay. So then we leave it here. So just introduced, continue it. Only for binomial. Okay. You can share for binomial in the group. We will see also how your binomial looks like. So we leave the calculus of limit and continuity here. When the lecture sheet comes out, we come back and add some more examples. Examples for today, we are coming from 1100 solution. Up to continuity of limits, this is enough for now. Okay, so binomial, you share the lecture sheet in the group so that you can look at it at some point. Okay, so for this night, you sleep well. And since you study a lot, study well, I'll get to your process. Bye-bye.